The next very important concept that we'll learn about is called the cumulative distribution function, in short referred to as CDF. Let's learn what CDF is, how is it related to PDF, why is it useful, and things like that in this section of the course. So let's go and see visually what CDF is before we go into code and things like that. So your blue line here is the PDF. Your blue line here is the probability density function. Your orange line here is the cumulative distribution function. Okay, for the same. So again, let me just put axes here. This is petal length of setosa flowers. Okay, so I'm just taking petal lengths of setosa flowers, and this is basically probabilities. Just to quickly recap, we know that PDF basically represents how many points. So for example, if you look here, right? So about 20% of the points typically have their petal lengths between 1.5 and 1.6, right? So this height represents how many points are there in this range, typically, right? That's what your PDF is. CDF says a completely different story. Let's see what a PDF tells us. So if you take a value of 1.6, so this is petal length, just to be clear, of setosa flowers. So if you take a value of 1.6, so this is our CDF, right? This function is our CDF, right? So let's see what is the corresponding value for 1.6. The corresponding value is roughly just above 0.8. So let's say this value, let's assume is 0.82. I'm just making approximations here. So what this means is, so let's write it in English because that's how we can understand it better. It means that there are 82%, 0.82 here. I'm just putting it here. There are 82% of setosa flowers that have their petal length less than equal to 1.6. This is what we can read of this plot. This is extremely useful information. We cannot get that information out of your PDF. This is your PDF, right? We can't get the same insight out of your PDF. Your CDF basically says, suppose for 1.6, the value here, corresponding value on the y-axis, the probability here is 0.82, right? So what that means is that 82% of your setosa flowers have a petal length of less than equal to 1.6. That's what it means. So first thing you'll notice as soon as you see this plot is it always starts at 0 on the left bottom and ends at 1 at the top right. Because what does this mean? This means that, so let's understand what this means, okay? Just using the similar argument here. So what this means is 100%, this is 1, which means 100%. It means 100% of setosa flowers have a petal length that is less than equal to 1.9. Similarly, let's take a value here. I'll just do multiple values here. Okay, this value seems to be around 0.15. Okay, what this means is 15% of setosa flowers have petal length that is less than equal to 1.3. Right? So what it's telling you is what percentage of flowers, any value here says what percentage of flowers, the percentage you can read on the y-axis, what percentage of flowers have a value less than equal to the corresponding x-axis point here. That's what your CDF says. Of course, nothing can have less than 0 probability and nothing can have more than 1 probability because all probabilities lie between 0% and 100%, right? That's what we can quickly read off a CDF plot. Now the immediate question is, how do you build a CDF? So we understood how to read a CDF, but how do you build a CDF? We know how to build a CDF, right? We saw that you can build a PDF by taking histogram and then smoothing it up. As I promised you, we'll learn about more how the smoothing exactly works when we learn Gaussian distribution. But for now, let's see how CDF is built. So let's take any value here, okay? So let's take a value of, let's say, 1.6 itself. Okay, so what is the corresponding point on the CDF plot for 1.6? How do I get this point? Okay, the way you get it is you say for 1.6, how many of your, so you have 50 flowers, right? These are your petal lengths of setosa flowers. Okay, so you basically say how many flowers have a petal length of less than equal to 1.6. And when you count of all your points, so you have 50 points, right? If let's assume 41 points or 41 flowers have a petal length that is less than, so let's say 41 flowers have 41 setosa flowers, that's what I meant. So 41 setosa flowers, let's say, have their petal length less than equal to 1.6. And our total data set is 50 points, right? So you divide 41 by 50, that gives you 82% or 0.82. And you put that on the y-axis. Okay. And you keep repeating this. You keep repeating it for 1.6, 1.65, 1.7, so on and so forth. And you get this whole curve, right? That's how you construct your CDF. It's basically for every value of your petal length or x-axis, you say how many points. So for example, if you take this, right? Suppose, for example, if you take, let's take 1.3. For 1.3, it looks like somewhere around 15% of points are below of setos of flowers have a petal length less than equal to 1.3. And that we can build it ourselves. That's one way of doing it. The second way is, we know that your PDF basically counts how many flowers are there in each, for each petal length, right? So this, I'm just plotting the histogram here. Okay, so you can plot a histogram like this, which we smooth to get PDF, right? So if you count all of them, so for 1.6, if you want the value for 1.6, you can simply sum up this plus this plus this plus this plus this plus this. That will give you this height. Okay, so it's basically a cumulative sum. So these are called cumulative sums. For any value x here, the corresponding value y, can be found using the approach that I just told you, which is 41 out of 50 case that I just explained a while ago. Or you can count all these, the heights of all of these probabilities that come before that, including that value. That's called a cumulative sum. And when you do that, you can understand what is, you can easily compute what is the y value corresponding to next coordinate in CDF. For those of you who know calculus, right, who remember area under curve, integration and things like that, if you don't remember or if you don't recall, it's okay. We will go over it when we learn calculus in more detail. But if you recall your calculus, basically if you have a PDF, right, the corresponding value of the CDF is basically the area under the curve, of your PDF till that point. That's what is your CDF, right? So if you differentiate your CDF, right, you get your PDF. And if you do integration on your PDF, right, you get your CDF. Those of you who don't know calculus or who have forgotten calculus, it's okay. This is just an additional point that I'm making here. We will learn some of these concepts when we learn calculus and optimization later in the course. So if you already know this, that's easy. If you differentiate your CDF, you get PDF, and if you integrate your PDF, you get CDF. Those of you who know calculus. If you don't know, it's okay. You can just look at the histogram approach, or basically saying how many setos of flowers have petal length less than equal to 1.6. Even that will give us how to plot your CDF. From a code perspective, it's very, very straightforward. We just saw the code for PDF, right? So till here is the code for PDF, right? So this is where I computed my PDF, also my bin edges. Here I'm using Iris Setosa dataset, and I'm computing the PDF on petal lengths with 10 bins. We saw how changing bins will change our plots. Now to compute CDF, it's just one line, literally one line. In NumPy, there is a function called cumulative sum. So this cum sum is basically cumulative sum. Cumulative sum. The word cumulative I used earlier, right? So if you take your histogram and sum up everything before that value, that's called a cumulative sum. A function cumulative sum in NumPy, when you apply it on PDF, you get CDF, and you just simply plot your CDF. It's very, very straightforward there. So this is all the code, literally one line to compute your CDF from PDF using a function called cumulative sum. And then you're just plotting it here, nothing fancy here. You're plotting your PDF and CDF as I've shown you here. So now the next question is, why is CDF useful? How is CDF useful for our Iris dataset? Let's look at it. So here I have plotted petal lengths. This is my Setosa, Virginica, and Versicolor, my 3 flower types. So these are the PDFs of my 3 flower types, right? I've also plotted the CDFs. So this is the CTF for Setosa. Let me just verify. So this is this is for Setosa, this is for Virginica. Just let me verify which is Virginica and Versicolor. I always get confused with that. So let's just go up and see, okay, where is my petal length? Here is my petal length. Of course, the second one is Versicolor. The third one is Virginica. Okay, so let me just put that in here. So this is my Virginica and Versicolor. Am I right with that? I hope, yeah. So I have my three types of flowers here. Just quickly going over, not to make a mistake again. You have your versicolor and virginica. Okay, sounds good. So let's go. So these are my three PDFs of virginica, versicolor, and setosa. If I mix these two things up, I'm getting confused. Sorry, bear with me. But just let's flow with the flow. So this is my PDF of setosa. This is my PDF of virginica. This is my PDF of versicolor. Right? Now comes the interesting part. These are your CDFs. Now I have a question. By just look, see, all these plots go from 0 to 1, 0 to 1, 0 to 1. Right? So I have one very interesting question. We said that to distinguish, of course, to distinguish setosa flowers, this is my petal length, right? I could say if the petal length is less than equal to 2, it is setosa. That's perfect, right? Because all setosa flowers have a value less than equal to 2. Because you see this CDF, you can say 100% of points, 100% of your setosa points or setosa flowers have a petal length of less than equal to 2. So you're done. So if you say if petal length is less than 2, then setosa. Okay, and you're going to be 100% correct with this because 100% of the points have a value less than this. Now comes the tricky case between virginica and versicolor. Now let's assume suppose I put a value of 5 as my threshold because that's where these two PDFs are intersecting, right? Now if I use 5 as my threshold, an interesting thing happens. Let's see what is the corresponding value of 5 here. The corresponding value of 5 for this CDF is it looks close to 0.95, right? What about this other one? Okay, let me just put it here. So this looks like on the y-axis, it looks like 0.95. What about this? This looks like 0.10. It's somewhere in the half line here, right? So this looks like 0.10 on the y-axis, okay? Now, if I say, if petal length is greater than 2 and petal length is less than 5, then declare it to be, I keep getting confused which is versicolor, which is virginica. Let's say this is versicolor and this is virginica. Let's just say, if petal length is greater than 2 and petal length is less than 5, then versicolor. If I say that, okay, and if I say if petal length is greater than 2 and petal length is greater than 5, let's say less than equal to, then virginica. Let's assume I've just written these two if-else conditions. So for setosa, it's very clear, right? For setosa less than 2, it's setosa. For virginica and versicolor, and virginica, let's assume I wrote rules like this. Of course, these rules are not going to be perfect because these PDFs are intersecting. But when I wrote a rule like this, I'm going to be correct with virginica 95% of the times. Okay, so this is going to tell me, this is going to be accurate 95% of the times. How did I say 95% here? Because if you look at the CDF plot for versicolor here, at the intersection point, which is 5, take the point corresponding to 5, go and check out on the CDF. This value corresponds to roughly 0.95, which means 95% of virginica flowers, right, of versicolor flowers have a petal length less than equal to 5. Which means 95% of my versicolor flowers will be labeled correctly. 5% will not be labeled correctly. Okay. Similarly, what about virginica? Now, virginica, I'm saying if it is greater than 5, only then it's virginica. Less than 5, it's not virginica. But there are 10% of points. How did I know about 10%? I looked at the CDF. Of virginica. And that CDF at value of 5 has the y-axis equal to 0.10, which is 10%. Which means if I use this rule, 10% of the times I'm going to make a mistake here. So here I'm going to be correct. I'm going to be correct 99% of the times and wrong or incorrect 5% of the times. Here 10% of the times I'm going to make a mistake for virginica and 90% of times I'm going to be accurate. 90% of the times I'm going to be right. So such an information cannot be understood from your CDFs, which you can use from your PDFs. So when you plot PDFs and when you're building simple models like this, simple if-else conditions, you can say how accurate your simple model, which just uses one feature, could be by reading the data off of your CDF, which you cannot get from PDF. That's one of the biggest use cases of CDF in data analysis and in modeling.